Hey wizards, welcome to your lesson for physics. In this lesson, we're going to be discussing Doppler effect. But what is Doppler effect and how does it relate to us? Now, Doppler effect might be a small section in physics, but it's a large section when you look at it in the applications in real life. Doppler effect describes the changes in frequency, either an increase in frequency or a decrease in frequency by successive waves. What that does is it enables us to look at sound and light and the changes with sound and light. The fluctuations of this frequency can be noted and is the foundation of Doppler effect. But where did Doppler effect come from? Doppler effect was a phenomenon that was described by an Australian physicist. His name was Christian Doppler. That's where Doppler effect gets its name from, because he discovered that the phenomenon Doppler effect described a flow of liquids or a flow such as velocity of blood, for an example. This phenomenon was described in 1842. But how does it relate to us now? Have you ever sat in traffic or been in a car when a police car or an ambulance was approaching you? Well, that's an example of Doppler effect. But how? Have you ever sat in the car and then heard the siren from a far distance behind you? It was quite soft. But as the vehicle approached you, the sound began to get louder and louder until eventually it was really loud when the car was directly next to you. What happened as the car moved away from you? As the vehicle moves away from you, the frequency of the car starts to get lower and lower. Therefore, you hear it differently. So we can describe that phenomenon as Doppler effect, where something appears to be a certain pitch or a certain volume or even a certain brightness, because Doppler effect applies to both light and sound. What else do we notice about Doppler effect? In physics, we do calculations involving Doppler effect. Those calculations allow us to look at the equation using the observer, which is usually stationary, or a stimulus such as sound or light, and we can do a comparison. In order for us to understand the calculations more clearly, we need to actually do some. So let's have a look at some calculations for Doppler effect and see if we've learned or truly grasped the concept of Doppler effect. So like we said when we discussed Doppler effect, we thought about a sound or a source, and then we looked at how it affects the observer. Remember that when we look at Doppler effect, we can see that this is emitting waves, and those waves are emitted. As you get closer to the observer will view more waves than it initially would have. Once it moves away, the amount of sound that the observer will hear will be less. So we can discuss that when we consider the sound waves with a constant velocity or a constant frequency and amplitude. The sound waves can be represented as concentric circles, as we can see. Those concentric circles represent a crest or peak as the wavelength radiates away from the source. This is because the wave travels away from the source in all directions, and the distance between consecutive crests or consecutive troughs in a wave is constant. When we learned this, we looked at the crests, which are represented by the black lines, and the troughs represented in orange. Do you remember us doing that video? This line would represent a black line, orange, black, orange, black, orange, black, orange, black, orange. The sound or the source, such as a police car or an ambulance, as we discussed, is in the middle or stationary, and then the observer can move closer or away. Or the observer can stay stationary and the source would move towards or away. When we have those instances, we can say that we can observe the change, the apparent as opposed to the actual. So what Doppler effect does is it measures the two. In order to do that, there is a formula or an equation that represents Doppler effect. That is FO is equal to Fs into V plus or minus VO, V plus or minus Vs. What do those terms mean? FO represents the observed frequency, so the frequency of the observed. Fs represents the source frequency, Fs. V is the speed of sound. Now usually we will describe that as 340 meters per second. We will assume VO is the velocity of the observer and Vs is the velocity of the source. Now remember, when we do calculations, we sometimes see that one or the other velocities will be zero. Or if both are moving, then you'll be able to put both velocities into a calculation. Now we must know that we don't actually need to analyze each case separately. What we need to look at is the relative motion between the observer and the source. So let's try to see if we can use our formula and discuss some examples. The first one says the siren of an ambulance emits a sound that has a frequency of 700 Hz. You are standing on the sidewalk. If this ambulance passes you at 20 meters per second, what frequency will you hear when the ambulance is heading towards you and when it is driving away from you? So, what is the first thing we need to do? The first thing we need to do is we need to analyze the problem or the question. Now, the question is asking us, what frequency are we going to hear when the source is moving at a certain speed? So what are we going to hear when it's moving away from us? What are we going to hear when it's coming towards us? We can immediately see that what this question is referring to is the Doppler effect. The values given in the question must be in SI units. So we can see that Hertz, which is the frequency, and meters per second, which is the distance or the speed, is in its SI units. Therefore, we don't need to do any calculation or any conversions. Step 2 would be to determine how we're going to approach the question. So we know that this ambulance is moving because it's moving at 20 meters per second. We also know that we are stationary because we are standing on the sidewalk. We are not moving. So if we had to look at the formula of f of the observer is equal to f of the source into v plus or minus v of the observer and v plus or minus velocity of the source, we can see that one of those should be 0. In order to correctly apply this, we need to look at whether all of the information that we have is valid and determines what signs we need to use for various speeds. Remember, this plus or minus means we need to determine if it's positive or if it's negative. So you as the listener are not moving. Remember, we said you are stationary. So you as the listener are not moving, but we have to consider the two different cases. When the ambulance is moving towards you, so let's look at towards. And we need to look at the situation where the ambulance is moving away. When we look at that, we can say that when we have been told the source is moving towards the observer, then we will use subtraction. Why will we use subtraction when it moves towards? Because the sound should be getting louder, not softer. So we'll use subtraction in the denominator. If it's moving away from you, the sound is getting smaller and smaller and smaller. Therefore, we will use addition in the denominator. So now let's determine what is the sounds as we move towards and away. So let's look at towards. According to our formula, what is f of the observer? You want to know that. You are calculating what frequency are you hearing. So you'll have FO equal to the frequency of the sound. We know the frequency of the sound is 700 Hertz. Into speed of sound. Do you remember we said that we're going to count that as 340 meters per second. Plus, what is my velocity as the observer? I'm not moving. So therefore my velocity is 0. All over 340 minus, remember we said it's minus the velocity of sound, and my velocity of sound is 20 meters per second. When I put that into my calculator, I get 743,75 Hertz. So when it's moving towards me, I'm actually hearing it louder than the frequency it's actually emitting. Let's look at what happens if I look at when it's moving away from me. Frequency of the observer, that's what I want to know, is equal to 700 into 340 plus 0 all over 340 plus 20. And that's going to be equal to 661,11 Hertz. Now I am hearing it much softer than I was originally. So can you see how it would change when it's coming towards you or moving away from you? You can quote that as a final answer and say when the ambulance is moving or approaching you, you hear a frequency of 743,75 Hertz. And when it is going away from you, you hear the frequency as 661,11 Hertz. Right guys, I hope that example was sufficient. I hope that you've learned how to use the formula for Doppler effect and you are able to apply that in various different examples. Remember to watch the next video where we discuss applications of Doppler effect. Also remember that you need to log on to our iWiz app, which is www.iwiz.co.za. There are worksheets with examples related to this section that will help you improve your knowledge on Doppler effect. And if that is not enough, log on to our app and register for a whole lot more. There are videos and lessons that will help you guide you through physics as well as Doppler effect as a topic. So wizards, get to practicing, and I hope that you would look at those videos and those worksheets. Good luck, wizards.